everyone, I'm Sonia. I lead the personalization team at the recommendations group. And in the next hour, I'm going to tell you a bit about collaborative models. Why do we want them in a recommender system? What are the challenges of incorporating them into the recommendation systems? And some examples. So let's start by what are collaborative models and why they're interesting in our setting. So in a sense, they're pretty complicated, but they're based on a very simple and intuitive concept. And this concept is, if my taste matches someone else's taste, then the stuff they like will probably interest me as well. Okay, so we have this example here. We have two guys. One is riding a bike. The other one is probably planning to ride a bike. And we can see that they're both like pizza, and they both like this weird salad. So we can actually use the likes of this guy in the black, dark blue shirt. The fact that he likes soda, we can use this information to recommend soda to this guy that rides the bicycle. Okay, so we see that they have similar likes. We can use information from one person to recommend items to the other person. So let's say that you have a set of items, okay? And for this set of items, you also have your users, and you have information about how your users interact with those items. So for example, here what I have is likes and dislikes information. And let's say that I want to sort of use this information to decide whether a new item is a good recommendation for my user. Okay, so whether user A that didn't interact with this item I want to know what is the probability of this user to like this item. So how to solve this? How to find this probability or this relevance? So essentially, the majority of these algorithms, they're generating a matrix, okay? And this matrix, the rows of this matrix are the users. The columns of this matrix are the items. And then they fill this matrix with the information they have. Okay, so remember this graph that we had. This is just basically all this information is encoded into this matrix. Okay, so so you see we have like a lot of information, but now we want to say something about user A and item I. So what we're doing is we're taking user A and we're finding a set of users in our data, which are kind of similar in terms of their interest or in terms of how they interacted with the items to our user A. So we found this set. We have C and we have B. Okay, because you can see that user C likes the same items user A likes, and user B likes this item and dislikes this item, which is exactly what user A does. Okay, so these users are similar. And then we can use the information from this user to say something about an unseen item, item I. So what would be your guess for dislike? Exactly, so yeah. So this is a dislike. How does it look in our setting? So I'm talking about items and users. What does it have to do with us? So in our case, we still have users, but our items would be the documents or the ads that we want to recommend that are in our inventory of recommendations, right? And our interactions are clicks. Okay, this is what we can learn from. This is what says that a user likes some recommendation, a user likes some article. But getting back to my example, so this was a pretty easy example, not just because it had like 5 users and 4 items, but also because this matrix is very dense, right? We have a lot of information here. So it was pretty easy for us to take a user and find a set of users that is similar to our user. But in reality, obviously in Outbrain and for other domains as well, for click prediction and for other domains as well, these matrices are much sparser. We don't almost don't have information. You can see like this matrix is blank. So it will be really hard from this type of data. It will be really hard for me to find this set of users which is similar to user A, because I just don't have enough data based on the raw clicks or the raw interactions of the user. And this is where embeddings come into play. Okay, so embeddings is one way of doing collaborative models, and this is what I'm going to dive into now. So let's imagine that we have sort of unrevealed knowledge about our users, okay? Something that we could have known, okay? Anyone recognizes this like feature space, this characteristics? Big five, exactly. So in psychology, you have something called the big five personality traits, and people are kind of classified into these personality traits, and you can say about any, about every person what is the mix of these traits that the personality has, or this person has. So let's say that this is your kind of, let's say that you know these characteristics about all your users. And I Googled basically extrovert celebrities, and I got Johnny Depp. So for example, for Johnny Depp, this would be our vector, okay, our vector in the space of personalities. So mostly extroversion will be very strong there, okay? And let's say that we have this kind of representation for all of our users. And imagine you also have the same knowledge about your items, okay? So, for example, there was an actual study in psychology that found out that extroverts, they tend to buy things that are related to experiences, like travel, food, stuff like that, not like materialistic stuff, okay? Because they like taking chances. They had like many explanations for that, but this is what they found. And so then, using this knowledge, you can take a recommendation. You can take like an article or an ad and say what mix of these personalities this ad has. Okay, so if I have an ad about travel, this would be the mix of personalities. This ad is good for extrovert people. Okay, and given that we have this information on our users and we have this information on our items, it's pretty easy to recommend stuff, right? Because then what we can do is just measure the proximity of this representations and say, okay, if they're similar, if this mix is similar for the user and their item, probably we have some relevance. Otherwise, if they're distant, then it would be a bad recommendation. Okay, so for example, I would recommend Johnny Depp this travel ad. I would not recommend this PlayStation ad. Okay, PlayStation, something materialistic. It's represented as different mix, and the similarity will be low, and this will not be recommended. And here we have an example of an explicit space that someone told us about. But the problem is that we don't know really how to find it, okay? We don't really, no one gives the space to us. And so the embeddings algorithms are actually algorithms that generate this space for us. And they generate the space for us based on this matrix that you've seen before of user interactions. Okay, so we kind of give the algorithm the raw data that we have, and we get as output this feature space. Now, it is not interpretable, okay? We cannot say what these features mean, but they can help us to make predictions, and I will show you how. So essentially, the input to the embedding algorithm will be our matrix of our set of interactions, and the output would be some, implicit feature space where every user will be represented as a mix of this feature space, and every item will be represented as a mix of this feature space. And the important thing about it is that the property that it has is that for users and items that they like, we will have a similar representation. And for user and items that they don't like, we will have a distant representation. Okay? And given that we have these embeddings, we are now able to say something about this user and item that they didn't interact, but we can say something by just comparing the embeddings of this user and this item. So how are we incorporating this into our serving stack? So just a quick recap about our serving stack. Most of you are probably familiar. So it is based on Elasticsearch, and I will start with the indexing part. Okay, so we have an inventory of ads and documents, and we want this inventory to be available for ranking in Elasticsearch. So what we have is indexer services that take all the ads and all the documents which are available, extract metadata for them, and index them into Elasticsearch. And what kind of metadata is being extracted? So we basically want to index all data which is relevant for filtering and scoring. Okay, so it can be the source of the ad, the campaign on the ad, the categories which are, for example, used for scoring, blacklisted publishers which are used for filtering. All this information is being stored into Elastic. And it's being done in cycles. Okay, it can be 5-minute cycles, 10-minute cycles, depends on the serving domain. So what happens in request time? In request time, we have a user coming in, and we have a context. Okay, so a context is basically information about the article the user is currently at. Okay. Okay. So the user and the context are the input to the recommendation service. Okay, so this is very general. This is both paid and organic stacks. Okay, so this is a very high level. And what the recommendation service is doing is basically taking this information about the user and the context and generating a query. Okay, query to Elasticsearch, and this query needs to encapsulate all the information that is needed, again, for filtering and scoring. Okay. And finally, we have the work Elasticsearch does for us, which is two main things. First, filtering. 10 times I've said filtering and scoring. So first is filtering. And for example, if we have an ad that blacklists a publisher, and our context is this publisher, if an ad doesn't want to show on CNN sites, and this user is coming from CNN, then this ad will be filtered out. Okay, so filtering is one thing. And then what it does, it takes all the eligible recommendations that are left and assigns scores to them. And this is done by a scoring script, which is a custom scoring script that we are writing. Elasticsearch has the option of basically injecting a plugin of our own code. So we are scoring documents and ads given the attributes of the document and the attributes of the user in the context. And finally, the most relevant or the recommendations that have the top score are returned to the user. Recommendation service and then the user. Okay, so adding embeddings to that is in a sense, it's very intuitive. What we need to do is two things. First of all, we need to index these embeddings vector to our Elasticsearch index, right? For every ad and document. And the second thing is we want to take this user embedding vector and send it in our query. And finally, the scoring script will take them both, compare them, compute the relevance, compute the similarity, and set the score accordingly. So we saw how our serving layer looks on a very high level. Let's see how we're generating the embeddings, and we'll then see everything together, and we'll talk about the challenges. Okay? So we're doing it with the embedding framework, and the embedding framework has several parts. The first part is an offline part. Okay, this offline part is based on Spark jobs that are actually running the embedding algorithms, and the algorithms are generating the embeddings for the user and the items. Okay, and as new data comes in periodically, we are retraining these embeddings. Okay, so this is the offline embedding generation flow. Now, the embeddings that are being generated by the flow, they're stored in Cassandra. Okay, each time a new sort of version is being created, it is stored in Cassandra. So the format is key value. We have a user, a vector, and then we had an ad or a document and a vector assigned to it. In a second, I'll talk. So no, it's not part of the user profile. Okay, and the next thing is a service which is the embedding orchestrator. And basically the goal of the service is to make these embeddings available for both the indexer, the indexing layer, and the serving layer. Okay? And what it does is regularly pulls data from Cassandra and checks whether a new version is available. If it's available, it loads it. And it has two endpoints. The first is get item embedding, and the second is get user embedding. Okay? So how are the different layers interact with this orchestrator? We have the indexer layer. that sends as input a document or an ad ID gets the embedding vector, okay? And very similarly, we have the recommendation service sending a user ID, getting the vector back. Okay, so how does it look with as part of the serving? We have this embedding orchestrator. As I said before, the indexer calls get item embedding when it indexes data about the document and the ad, and then it can actually use this item embedding vector as another property of the ad that it indexed to Elasticsearch. The same thing happens with the recommendation service. In addition to all the data that is passed from the user in the context in the query, we also add the embedding vector. And our plugin now needs to support the computing this distance. So we can use this relevant score either as our final score or as an ingredient in our final score. Okay. Challenges that I'm going to describe. So two of our main challenges are, first of all, the dynamic nature of our users. Okay, so our users change basically with every interaction they make, and this is how our user profile is built. It actually changes with every page view of the user. So we'll see why this is a problem. And the second thing is versioning. Okay, so in addition to the fact that our user change, our whole feature space can change over time, and we'll see why this can be problematic and how we should handle it. Okay, so let's start with the first challenge, dynamic nature of our users. And I'll start with a very simple example. Let's say that we have a very small feature space, two features, okay? And we don't know what they are, but let's assume that the world has two kinds of people, okay? We have happy morning people and cranky morning people, okay? And this is what our algorithm found to be like the most distinctive thing, the most predictive thing of clicks. Let's say that we have this user that at the time the embedding was generated, he got this mix. Okay, so pretty cranky morning user, probably based on the fact that this, most of the browsing history is based on nightlife and stuff like that. Okay, but this is what the algorithm found. Now, over time, or essentially with every page the user does, stuff can change. So suddenly, this user is very interesting in those articles. Morning yoga, morning joggling, and stuff like that. So now the question is this user still a cranky morning user? And the thing is that if we were able to actually retrain our embedding with every new page view a user is doing, this would be solved, right? But it's something that is not feasible. Okay, this is an offline stage. It can take several hours, and we have a new page view for, we are very frequently seeing new pages for our users. So how can we actually make our embeddings dynamic? And the solution here is related to the questions that Guy had before, is using indirect embeddings. Okay, so what are indirect embeddings? Instead of just taking the UUID and representing the UUID as a vector, we are using the user profile ingredients to generate our embeddings. Okay, so we kind of learn embeddings for the traits of the user and not directly on the user. For example, categories, the entities, the actual last pages of the user. And by doing so, I'll show you how we can keep the embeddings dynamic. Okay, so we train these ingredients based on our features, and then what happens in serving time is that we aggregate, we combine the embeddings given the current state of the user, given the current user profile, we combine the relevant embedding into a single embedding, and this is the embedding that is being used. So, okay, so you remember from before, we have our offline flow. It generates, in my example before, it generated embedding per each user. Now it generates embedding for each user feature instead, okay? And again, it stores them to Cassandra. Everything is very similar to the way it was before. But now the embeddings orchestrator has to have this aggregation logic in it. Why? Because what's happening in the server layer is that instead of sending the embedding orchestrator a UUID and just getting the vector like a lookup, we are sending a set of features of the user. And then the embedding orchestrator aggregates them and returns back a single vector that is then being used. Okay? So in our example before, what's going to happen is that, first of all, we're not embedding users. We're now embedding, in this example, we're embedding pages. So we can say about each article what is the mix of our two features for this article. So we can say that this like nightlife thing is a cranky morning user. Good morning yoga is much more happy morning person, and jogging is much more happy morning person. And then when our user has this new interaction of good morning yoga and the jogging, we can actually aggregate them in serving time and take them into account. And then our embedding is not stale, it changes with the pages the user has. So second challenge is versioning. Okay, so versioning is not only supporting changes in the user, but actually supporting changes in our whole feature space. What does it mean? Let's say that at some point of time, the algorithm thought that this was the most informative thing you can say about our user and their items. Okay, how they behave in the morning. But then you have midterm elections coming in. And when midterm elections come in, maybe the most distinctive thing you can say about users is whether they are Republican or Democrats. And this is something that is most predictive for how they interact with our content. So this is automatically captured by the embedding algorithm because we give it new data all the time and it retrains. But the danger in that is that we have to have a match in the version that we have on the user side and the version that we have on the item side. Okay, this is pretty obvious, right? We don't want to compare like apples to oranges in this setting. But why would we even have a discrepancy in our version? So let's look at the following scenario. Where can we have a discrepancy? So let's say that a new embedding was created, okay, by the offline layer. The serving layer like immediately catches on, starts using this new embedding, but the Elasticsearch has a certain length of indexing cycle, right? So it starts to kind of use, index this new embedding, but obviously it takes time for the full index to have the most updated embedding. So at this intermediate stage, what we'll have is corrupted relevance score because we're going to compare. I mean, they're both of size 2, but they are completely different, have completely different interpretation. And we want to avoid that. So how are we avoiding that? What we do is we store 2 versions in our embedding orchestrator. One version is the latest version. Okay, this is the version that is the most recent one, generated by the offline layer. And the second one is called the in-use version. And the in-use version is the one that the system sort of knows that it exists in all the items of our index. Okay, that it is safe to use this version in our serving time. And in a second, we'll see how it's being set and how it's being controlled. But assume that we have the state of an in-use version. Okay, so I'll show. So in this example, we already have a new version, okay, from the 26th of November, but our in-use version is from the 25th of November. And this is the only version we can trust to exist on our index. So given that we have this knowledge that the in-use version exists throughout our index, we can instruct the recommender service to always use the in-use version. Don't use the recent version, use only the in-use one. Okay, so it means that when it goes to the orchestrator automatically returns the vector of the in-use version and not the latest one, even if it's not the most updated. So we care more about the match than to have the most fresh version. And now the question is, how do we actually maintain this state? right, of this in-use version. And we have two scenarios, which are different for the paid stack and for the organic stack. So for the paid stack, we have what's called the shadowing indexing strategy. What does it mean? A shadowing indexing strategy means that we maintain two indices. One is live, and it's read-only, and this is the index that the serving layer is querying. And the other one is in progress; it's building in, behind the scenes. The indexer can index to this in-progress version, and once it is ready to use, we're doing a swap. Okay, it's an atomic swap. So in this setting, how do we maintain this in-use version? What are we doing? So the indexer cycle looks as follows. Okay, the cycle starts, we want to index all our ads. So this is the paid service stack. So we want to index all our ads into Elasticsearch. So first of all, the indexer extracts the latest version, okay? It wants to be as fresh as possible. It extracts the latest version from the embeddings orchestrator. And in this example, the latest version is from the 26th, okay? Second thing that it does, for each ad, it asks for the embedding of that version, of that latest version, okay? And indexes this version into Elasticsearch. Now remember that this index that we're now filling, it's not currently used by our serving layer, so we can do whatever we want there. And the last step would be after the cycle is finished, after all the data was indexed for our ads, we set the in-use version to be the latest version. Okay, so we're making sure that from now on, this is what the serving layer will do, and the flip is happening. So basically, now this version is in use, we can use it in serving time. So the more complex scenario would be in our organic stack. And why is it more complex? Because we have an incremental indexing strategy. What it means is that we have a read-write index. And that means that we are constantly updating the document in this index upon any change that appears in the document. Okay? And then the problem is that when there's a cycle of such updating, we can have mixed versions in our index because some were already updated with the most recent version and some were not updated. And this is not a standalone index that we're not using. This is actually our live index that we are using. Okay, so we can't afford to have this mix. So the solution here is that in the organic stack, we are indexing two versions. Okay, so one is the in-use version, and one is the most recent version. Okay, so this way we make sure that at each point of time the in-use version exists for every item that we have in the index. Okay, so what we didn't cover, we can do it offline if you have any questions. How do we handle A/B testing? So for A/B testing, we want to evaluate multiple embeddings in parallel. Okay, what is needed for that? Cold items, questions that got asked before, how are we handling those? And multiple embeddings for user, it's a use case that we also support. So this is currently in production, and we're using it to test different collaborative models.